Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Shimon Ullman on object recognition, and we spent a nice hour chatting about his earlier work writing MMX and SSE code for real-time denoising of images, which is kind of cool. And he did his grew up and did his undergraduate work in Russia, and which I guess. It's still part of Russia, right? They're never going to break that part off, right? It's not that far from the central part of Russia, but I mean, it's far from the central part. And now he's here visiting us and be finishing his PhD in a matter of months and not years.
A few months.
Great. Thank you very much.
I hope so. Thank you very much. And it's an honor for me to be here. Today I'll talk about object classification by hierarchies of semantic features. This is joint work with my advisor, Professor Shimon Ullman. But first, before talking about my work, let me review some basics of fragment-based image classification. So, as an input, we have a training set consisting of subset of class images, images depicting the object category that we want to recognize, and non-class images, just background. And we would like to, given a novel image, produce the class label, whether it belongs to the object category here or does not. How do we do it? As features, we use just rectangular row patches of image intensities. And in order to generate informative features of this type, we first generate a large pool of candidate fragments of different sizes and positions from the class images. And then, for each candidate fragment of this type, we correlate it with both class images and non-class images. And then we compute the optimal separation threshold between the correlations with the class images and correlations with the non-class images. And the criterion is just the mutual information between the C, which is class variable, 1 here and 0 here, and F, which is a function of theta, of threshold. This is the detection variable. It is 1 where the particular image has correlation greater than the threshold, and 0 otherwise.
So, just a quick question. Is
yes.
that the same thing as the minimum error criteria, or? No, it's not. It's not quite the minimum error criteria, right? How intuitively, how would you relate those two in terms of what threshold you would get?
Oh, this is very simple. Suppose that our threshold is very low. Okay? Then we'll get lots of false alarms. On the other hand, and this will obviously make our mutual information low.
But also will make the number of errors high.
Excuse me? Number?
So one could pick the threshold based in another way, let's say, as the minimum
Lots
error
of ways.
criteria.
Yeah.
So all I'm saying is if you have many false positives, you would have many errors, right?
Exactly. So there are several ways to do it.
Okay.
That's right. We chose the mutual information way. Okay. Now, it's not even we. Okay. This is the previous results of Shimon and some of his students. Okay.
Right.
So I'm just reviewing the basic algorithm, and then I'll show the extensions. So having chosen the optimal threshold and computed the corresponding mutual information, we can rank our fragments and select first the most informative fragment, and then successively select more and more fragments that bring the most additional mutual information to those already selected here. It's just a greedy procedure of selecting more and more fragments into our set.
So can I look at that equation real quick? So this is the max over the min?
Yeah, I can explain it if you want to. So let's suppose that we have this fragment as a candidate.
Right.
What do we do here? We go over all the fragments that are already selected. Okay, we know the mutual information of them. Okay, And then we can compute this mutual information. It is the mutual information between class variable and joint between the detection variable of this fragment already selected and the test, the candidate. Okay? And then we see the additional mutual information. So how much this T adds to the mutual information. Okay? And of course, we look at the fragment that we add the least amount to it. Okay? So even if this minimum is more than other functions of such type from other fragments. So if this minimal amount of mutual information that a particular candidate adds is maximal, then we choose this one. This is the intuition. Okay, it's once again it's not optimal in the global way. Okay, but then we cannot estimate it using joint of all the variables. Okay, because it would take the enormous size of of training set to do it.
Sorry.
Yeah.
What's the complexity of this algorithm then?
You mean computational complexity? Let me see. It should be n square.
I have a question. I mean, is there a reason? So what you're trying to do is you're trying to pick the next fragment.
Yeah.
I mean, why not pick the next fragment as the fragment which gives you the most gain over all the other fragments that you've picked already? So you seem to be picking this in this criterion, which is, I mean, you're looking at like a pairwise criterion between the fragments that you've selected and the new fragment coming in. Why not just look at the entire set of fragments that you've selected and then pick the next fragment which gives you the most information gain?
Because if you are looking at the entire, you mean the entire set of this one, okay? So kind of computing the mutual information between class variable and joint of all those variables. It's impossible to estimate. As simple as that. You have too many variables here, okay? With the limited size of training set, it's impossible to estimate. It will be very rough estimate. So can I move on? And having selected this set of informative fragments, we can use, for example, just the naive-based classifier. We can use other classifiers as well, but the paper that I mentioned, it's Ullman Vidal Naquet 2002, shows that using more sophisticated classifiers does not add to the recognition performance. This is because the features are informative enough. So this is kind of basic approach. And now I'll show for the bulk of my lecture, I show two ideas to improve this. And then I'll show the convergence, I show the fusion of those two ideas. And then maybe a little something additional. So part one, hierarchical features. In the algorithm that use this approach or similar approaches, we represent objects as a collection of informative parts. Now why not take one step further? Why not represent the parts themselves as a collection of informative subparts that are optimal for recognizing these parts? And this idea can be taken recursively, thus producing the whole hierarchy of parts, subparts, subparts, and so on and so forth. And the motivations for such process are twofold. First of all, we gain additional flexibility because for every subpart we allow a small amount of independent motion. Thus, we can instead of detecting the part using the rigid template, now we find it using a set of subparts, and every subpart can move individually. Therefore, we can detect it in much more situations. We can be tolerant to much more, geometric changes and changes even in lighting. And the second reason is biological motivation. There exists substantial amount of evidence that information in visual cortex is processed hierarchically. Therefore, it's interesting to see whether we can, come up with some computational scheme that also mimics this way. It is not what what I'm showing here is not exactly, biologically grounded. We cannot do, in a simple way, we cannot do such computations that I will be showing. But still, this hierarchy can be adopted to, to biologically plausible machinery. So how do we construct the hierarchy? We start with one of the informative fragments. Okay. We compute the optimal threshold, and then we should define the training set. Basically, we want to apply the same basic algorithm, but to the subfragments, to selection of the subfragments of this fragment. And to be able to do this, we need to redefine our training set. We need, in the positive part of the training set, we need the instances of this fragment in various class images. And in this part, in the negative part of the training set, in principle, we could use any patch from the background. But only those patches that are substantially close to non-class boundary are interesting. Therefore, we use false alarms as our training examples. Okay? This is also very well-known technique. Nothing new here. And if we want to somehow enrich our training set, we can lower our threshold somehow and use fragments that are detected using this lower threshold. Having defined our training set, we can use exactly the same basic algorithm. So we start with extraction a large pool of candidate subfragments from our fragment. Okay, now we restrict ourselves to subfragments. And then, using this max-min procedure, we can select a set of subfragments that are informative for the detection of this fragment. Next stage is parameter optimization. I'll cover this a bit later. And then we check the stopping rule. The stopping rule says whether we should keep this set of subfragments, or maybe we should discard it and use only the fragment as a whole, because somewhere we should stop our hierarchy construction. We cannot break it down to the pixel level, because pixels are not informative. They can be matched to everything. Okay? And the stopping rule that we use is very, very simple. Basically, what we do is we check the classification performance of the whole hierarchy with these subfragments and without them, meaning with this fragment. Okay? And we compare the recognition performance. If the recognition performance using subfragments is better, we keep them. If no, we stop the subdivision, we keep this fragment as our node of the hierarchy. And this we do for every informative fragment that we had in our original set, thus arriving to the whole hierarchy. And for each subfragment we repeat it until the stopping rule tells us not to do it. This is the hierarchy. Now for the parameters. One of the most important parameters for this process is so-called ROI, region of interest. Region of interest is simply the search window where we look for the match of the fragment in the novel images. And of course, for the subfragments, the ROI is set relative to the position of the fragment. Now, why ROI size is important?
Quick question?
Yeah.
So just a more basic question. So for the fragments themselves, before we started to do the subfragment, do they have regions of interest, or do they look throughout the entire image?
They also could have region of interest, yes.
So you might say, look for the left eye on the left side of the image or something like that. Is that typically done, or does one typically just go ahead and let them look everywhere?
It is typically done, yeah.
I see. So that's a part of the learning you just you didn't discuss, but that's because that's not your work. That was somebody else's work.
No, that's not because it's. I did not discuss this in the introduction.
Yes.
Simply because it was not published there. Okay, it's part of my work. Okay, this ROI simply it is applicable to the basic level as well.
As well.
Okay.
Okay.
So if ROI is too small, once again, if ROI is too small, then we have many misses. If ROI is too big, we have many false alarms. So there exists a golden middle, somewhere in between. And indeed, we are able to find it. Here I show the plot of mutual information of some typical fragment as function of y and x size of the ROI. And you see that it reaches a maximum at some intermediate point. So we can find it. Here I show some ROC curves. This is ROC curve curve of a fragment. This is a ROC curve of a classifier, of course, okay, based around just one fragment. This fragment was looked over the entire image. Okay, here we have some ROI, okay, of sensible size, okay, 32 by 32, which made sense for our data. Okay, and here I show the ROC of the optimal ROI. So there is an improvement.
So this kind of is in fact kind of related to my question, because this is an ROI that you've done for the fragment rather than the subfragment, or are you doing it?
For this illustration, it was done for the fragment, yes.
So for example, this might be, as you just showed in the previous slide, like learning that the left eye should be shown over on the left side of the image.
Yeah, something like
What
this.
I don't quite understand is the blue curve. So the purple curve is after learning, right?
Yeah.
For something. And
Yeah.
what's the blue curve?
The blue curve is just, we took some size of the ROI, which made sense, just from looking at the data.
I see.
Nothing more, nothing
And
sufficient.
the ROI parameters are not just the size, but also the center of the box, right?
Yes, yes.
Or it's the corners, whatever. It's more parameters.
It may depend. Let me say so. It can be learned this way, okay? Under some assumption, okay, you can do away with just two parameters, because you know where, for example, if your data is tightly cropped around the object,
Okay.
and of course you know where your fragment, your original fragment,
Okay.
comes from,
Right.
then you can center the ROI around this fragment. Okay, so you need only two parameters in this case.
Right. But you might have some fragments which occur in the same place every time, and then others, like, I don't know, like the hand or something. Let's imagine you build a hand detector. It could be anywhere, and then
Right.
you wouldn't necessarily. So you're saying that
So
you would just
in
learn
the
that the thing should be big, but it's still centered where you originally detected it. So in other words, the center is not so interesting because you just learned to expand this thing to include the entire image.
Well, it depends, okay? It depends on the scenario.
I see.
Okay, so having done all this, we can produce our hierarchies, okay? In fact, there is one more set of parameters, but I will be covering it when I'll be talking about the classification, okay? So there are some examples of the hierarchies. Here I stopped after the first level, okay? So it's not that we cannot produce more, just.
So the output of this process is
Yeah.
you start with a fragment.
I start with a collection of the fragments, okay? For a particular fragment, I show how to build it, okay? You can build it for every fragment you have, you determined as informative,
Yes.
okay? So you are, in a sense, you are left with a forest, okay? Every forest is a tree that you obtain from and then you can kind of combine the roots of those forests into a new root that is responsible for the whole object.
Can we go back a slide just to look?
Yes.
So in this case, these are little pieces of a particular car, right?
Those are this car. I just show the simple concrete example of the object from the category,
Right.
because you can see here that wheels are not the same. Okay, they come from different images of the same class.
Can we go back one more?
Yeah.
So this Virgin Atlantic plane, that's the fragment that you've picked, and it's useful because it's good at distinguishing planes from non-planes.
Right.
Virgin Air. But then you want to further decompose that one fragment into subfragments, and are those always actual pieces of the original fragment, or can they be actual pieces of other fragments?
Good question. For this particular work, they are pieces of the same fragment. Okay, and I'll show later how this can be extended.
I see.
But the question is right. So, the classification. In general, many methods can be devised for the classification using such construct. Okay? For this particular work, we used a very simple scheme that similar in spirit to the lower unit of the HMAX scheme. And it's simply the alternating layers of maximization and summation. And here I'll show a little demonstration how does it work. Suppose that our hierarchy consists of a parent fragment, the bluish here, okay? And it is represented in terms of his two sons. That's all. Now, if we were using the parent fragment as before, just as a rigid template, we would go over all the locations within its ROI, compute some measure of visual similarity, for example, normalized cross-correlation, and pick the maximum. And then we would compare this maximum to a threshold and arrive at a decision. But now we are representing this parent fragment in terms of his two sons. So how do we do it? Let's suppose that the parent fragment is in a particular position. Okay? Then, having fixed its position, we also fixed the ROI windows of its sons. And then we can find maximal correlation within those windows. Then what remains is to combine those two responses of the sons. Okay? We do it in a linear way, okay? Plus some bias weight, obviously. And then we feed this combination to a sigmoid function to soft threshold it and normalize. And then this SP, this response, is the response of the parent fragment for a particular location. Now we can, as before, we can go over the locations, repeat this process, and find the location that gives us maximal response. Of course, I'm describing it here like top-down. Okay? In practice, it's done efficiently. It's done bottom-up using dynamic programming.
So the true score of the parent fragment has really got nothing to do with the parent fragment. It's got to do with its children. Or is there a component?
If you suppose that children are totally unrelated to the parent fragment, yes.
Well, no, I don't see a component here which might have to do with the parent fragment as itself. It's just related to its children. Is that right, or am I missing it?
You are completely right.
So you don't. So you could actually add a score which was a function of the parent fragment itself.
You mean add the score that is related to the correlation between the parent fragment template? We could have added it. Moreover, we did such experiments. This does not improve the recognition results.
I see.
Yeah.
Do you do anything to make sure that the children cover, their template size covers the entire size of the parent? Or can you allow, like in this case, you just have two children which are a small subset of the parent?
The question is, the answer is the following. Okay, we have several, when we use this max-min algorithm, to select more and more informative fragments, then we need to stop somewhere, okay? Because at the end of the day, every additional fragment can improve mutual information. If you look at the mutual information between class variable and the joint, okay. And the stopping criterions are: first, if the fragment does not provide, the amount of additional mutual information above some threshold, then we stop the process, okay. So it could happen that only a few fragments that do not cover the parent fragment entirely are selected. Okay. On the other hand, sometimes it so happens that there are more informative fragments, and then we use additional criterions like number of fragments or the sum of their areas, something like this. Okay. So in principle, it could happen that a fragment, if we are not careful in the selection of the parents, it can happen that a single child is more informative than this fragment. Okay, so it can happen. Okay, it does not decrease the. Okay, so this is classification, and yeah.
Just to compare it to the approaches which use elastic nets or something like that, where you basically say the center point of the matching subfragments are related through some covariance distribution, right? Mean and covariance. You don't have anything like that, right? It's just the ROIs that encode the.
You can view these ROIs as uniform distributions, right, with these bounds. Yeah, okay. But I must
uniform and uncorrelated and independent, right? Because if one thing ends up in the lower right-hand corner, it has no preference for its other sibling to end up in the lower right-hand corner, right?
Quite right. Yeah. But I must say that this is the particular way of modeling these geometric relations. Okay, hierarchies are able to do more than this. We we are able to incorporate Gaussian geometric relations in this. In fact, I have the implementation of this one. Okay, so this is true, throughout the entire talk. I'm talking about the specific implementations of those particular papers. Okay, now we have extensions of everything. So this is the ROC curves, and first of all, the blue one here. Okay, it's the ROC curves of a classifier built around this very fragment. Okay, just a single fragment classifier. Now, the black one here is the ROC curves of a classifier based on the first level of decomposition. So we forcefully just stopped the decomposition after the first level was obtained. Okay, and the red one is the hierarchy, is the performance of the whole hierarchy. Okay, it stopped whenever it wanted to stop, using the stopping rule that I described. So you can see that we get an improvement. Okay.
What's purple?
I'll cover it right now. Okay.
Right.
So and I must say also that people asked okay, this is the one fragment classifier. Maybe if you use several fragments, okay, then you do not have this type of improvement. Maybe it saturates, Okay, and the answer is no. In the paper I show, it's last ICCV paper. Okay, I show examples of classifiers built around tens of up to 50 fragments. Okay, and I show that there is no saturation. Okay, that the hierarchies are consistently better. Now to the purple one. Purple one is interesting because we asked ourselves, okay, here we painstakingly optimize all those sizes of subfragments and sizes of ROIs and so on and so forth. What if we would simply subdivide this one in a regular fashion? Let's say 3 by 3 or something like this. And also, what if we give this one and its subfragments give a fixed ROI? Maybe it would be enough. Okay, maybe this hard work is not necessary. And the answer is not. The answer is that using this regular subdivision can even hurt the results of a single fragment classifiers. This is also very consistent. So I see it almost on every run of this comparison. Okay. Now, part of the explanation of this, by the way, is because our initial fragments are very informative. Okay, for fragments that are not so informative, okay, the regular subdivision could improve the results. Now, this is another claim, the claim that hierarchies improve rotation scale tolerance. Here I show the plots of the ISO equal error rate lines, okay, as function of rotation and scale. And here's the performance of a single fragment, and here's the performance of a collection of its subfragments. Okay, and you can see that both the performance is better and the tolerance is improved. So those lines are wider. Now, here I show the examples of atomic fragments. By atomic fragments, we mean the fragments at the very bottom of the hierarchy, node fragments. And as you can see, the atomic fragments are not class specific, which is obvious. And that they can be grouped into clusters of simple edges and bars, termination corners, and complex, we call it, just textures or whatever. Okay, and this gives us some hope to arrive at a universal alphabet of vision. Okay, which can be very helpful because people often build their recognition systems, from bottom up. I mean, they start with the set of like Gabor-like features or whatever, and then combine them. Okay, and here we show simple process guided by very simple measure mutual information that starts from the objects, whole objects, and arrives to those features. Okay, which are useful for recognition. Okay, There are other properties of these atomic fragments, but it's out of scope, I guess. So, conclusion so far. Hierarchical features are more informative than the holistic ones. Hierarchy construction is a top-down process. Classification is a bottom-up process. Only the atomic fragments, the nodes, are directly correlated with the image. From there, we only combine their responses. Subfragments' position, sizes, and ROIs must be optimized. Typical hierarchy depth is from 3 to 5 levels, okay, which is in accordance to some biological findings. And last, high-level subfragments are class-specific, low-level are shared between classes. Yes?
Since you're just matching these smaller fragments, is this a lot faster computationally than doing the original method?
Yeah.
So this algorithm is much faster than the original method. Okay.
So, the second idea to improve the basic algorithm, we call it semantic equivalence. And let's suppose that, once again, we have a set of class images as our input, and just one fragment, we call it a root fragment, that depicts some part of the image. And we would like to get this set of fragments as the output. Fragments that depict the same part of the object, and maybe not visually similar to this one. Okay, and why would one want to obtain such thing? Motivation, once again, comes from the recognition. Okay, if this is our classifier, okay, we would like to improve its performance by including more appearances of parts, something like this. Okay. And one can say that using your greedy procedure, max-min procedure, okay, you constantly adding more and more fragments, okay, and with the time, you'll have enough pictures, you know, of eyes and of mouths and so on and so forth. So why not simply use this in a naive-based classifier? And the answer is we can do it, but the performance gets hurt, because the naive-based classifier assumption, conditional independence given the class, gets violated. Therefore, we must identify the different appearances of the same parts and group them before we feed them to the naive-based classifier. This is the idea. Now, how do we do it? The idea is very simple. Let's suppose this is our root fragment, and we want to detect its semantic equivalent mouth in this image. Okay? But we cannot do it by simply visual similarity, because this is visually dissimilar. But suppose that we also have several other fragments that can be found here by visual similarity. Then we can conjecture that the fragment that possesses the same geometric relations to these guys as this fragment possesses to these guys should be semantically equivalent to this one. This is the idea. Now the question is, how do we find such context fragments? We call, once again, this is a root fragment, this is semantic fragment semantically equivalent to the root. And these guys are context fragments. Okay? But before I show how do we do it, first some assumptions. And once again, these are assumptions only for that paper. Now we have much more sophisticated model. So assumptions are no large variation in scale rotation of viewing direction. Second, context fragments are conditionally independent given the root fragment. Probability distribution of coordinate differences between a root fragment and the context fragments is two-dimensional Gaussian. And the prior probability of detecting the root fragment in the absence of the context fragments is uniform. That's it. Now, the workflow. We start with the root fragment. And first of all, we find the subset of our input images where this root fragment can be determined by visual similarity. This is the first step. Now, from these images, we extract, once again, a large pool of candidate context fragments. And then we select good context from those. And using context, we find in the original set of class images fragments that are semantically equivalent to the root. And then we do some processing. So this is the workflow. This step and this step are trivial. So the first question is here, How do we find good context fragments? What is a good context fragment? We pose two criterions. First of all, it should co-occur often with the root fragment. And the second criterion is that not only it should co-occur in a stable geometric relation. So the variance of coordinate differences should be small. Okay? Having these two inequalities, we can sift out some of the fragments. And for the rest of the fragments, we want to rank them. So to find the best context fragment, and so on and so forth. And we simply combine these two requirements to get we call it consistency weight, the weight of contextness.
So over what distribution are you evaluating these probabilities? So is this the distribution of class examples or class and non-class examples?
No non-class here.
I see.
There is no non-class. Only class, empirical distribution. Yeah.
So this set, images where the root is detected, is a subset of the class examples.
Yeah.
And are those distributions on the next page on this subset or on the whole class?
On this subset. On this subset, yeah.
I see. So for this particular case,
because you see here is given FP.
So we know P of F here is 1 because it has everyone has it. It was detected. So basically what we're looking for are fragments which occur commonly in that subset. That's P of little f.
No. P
capital F here. I mean, because can we assume is always true because that was where all these images have capital.
Let me just a moment. Let me correct myself. Okay? This one is evaluated on the subset, but this one is evaluated on the whole set of the images. Okay?
So
of the class images because P of F exactly 1 here.
Okay. So let's read that out as in English. So that says the probability that I find the mouth, given that I found the ear, let's say, is greater than the probability that I found the mouth in this distribution of class.
So it says, by the way, the algorithm works fine even without this. Okay? So it's a nice addition, but even without this, it's robust enough to cope with this. Okay. But basically, you say that this one can be used as predictor for this one. Okay. So if you find this one, you can say that the probability of find this one is bigger. That's it. Okay. So the process is very simple. We first of all we remove the candidate that do not meet our criterions. You remember the co-occurrence is low or the variance is big. Then we select the candidate fragment with biggest consistency weight, the best context fragment we have. And then we eliminate those fragments that intersect it because we want to maintain the assumptions of conditional independence. And then we repeat those steps until we have candidate context fragments. The set of candidate context fragment is empty. And now we can estimate once again on this small subset, not small but subset, okay? We can estimate, since we have detected their contexts and the root fragment, okay? We can estimate the parameters of Gaussian, okay? That's it. So now the question is, how do we use context in order to find the fragments that are semantically equivalent? This is very simple. Let's suppose this is our novel image where we want to find the semantic fragment. We found here context fragment C1. In general, we will find here a subset of the whole context set because occlusions or something. Okay? So we found it in the position here. Okay? This scheme for this paper does not incorporate multiple matches scheme. Okay? Now we have it implemented. So it predicts the position of the fragment that is semantically equivalent to our root fragment. Okay? And we also know the uncertainty, we know the covariance matrix. Okay? The same is for C2 and C3. And since we have the fully defined probabilistic model, we can go and find the coordinates xy that maximize the probability of the root fragment. given the coordinates of the detected the context fragment. Okay, and we do this. Okay, here I show the simple demonstration. You can see that even using the first fragment, okay, they are not used sequentially. Okay, they all used together. Okay, it's a closed form solution. Nothing to iterate here, but I just show, okay, by addition one by one what happens. Okay, so here nothing much happens because even the first fragment was good enough. Okay, we brought our prediction in the close vicinity of the ground truth. Okay, but we can add more and more. Okay, not always it improves, but it does not hurt much. Oops. So here it is. And the last step is the post-processing. Yeah?
Quick question. Do you make the assumption that your analogy, like the features that you're trying to find that are semantically equivalent are the same size? Cover the same area?
Because we assumed no large variations in scale.
Okay, so
for this work, yes. But again, we have now elaborate model there. Since we predict in the scale, we can scale the. Okay. So the post-processing, it's optional, but those 3 steps are common enough to mention them here. So first, we remove semantic fragments with low maximal probability. Low maximal probability means that very few context fragments were detected, or maybe their evidence was contradictory. Second, we remove semantic fragments that do not belong to big clusters. This is because, for example, we are looking for a semantic fragment of a mouth. There are several variations in the appearance of mouth, but not so many. Therefore, they should cluster well, using simple visual similarity. And then, those that do not belong to one of the big clusters are probably outliers, so we can throw them out. And last is to choose a representative semantic fragments. We don't want to use 100 semantic fragments in our classifier for several reasons, obvious. Okay, so we find, once again, greedily using mutual information, we find, for example, 5 best or 20 best, whatever. Here are some examples of the obtained semantic fragments. Those are roots, and those are fragments that are semantically equivalent. You see that appearances can vary rather wildly.
Does that ever fail?
In what sense?
Well, just what's the worst it's ever done? I mean, because it seems to me that there could be cases where, for some reason, it's not detectable enough, or something like that,
and
then
you're right.
It'd be interesting to see, because this kind of it suggests a kind of a bootstrapping process or something like that, and so the question is, how often would a purely automatic bootstrapping process kind of lead to something reasonable?
I'll show you in a moment the detection percentages. Okay, so you'll see the probability of errors, at least on our test data. Okay, so here are some more sets of semantic fragments. Here, okay, we used this algorithm, okay, as a part detector. Okay, simple setup of part detection. Okay, and here I show you the part detection by this algorithm and the part detection using visual similarity. The NCC means normalized cross correlation, but applied to images that were DOG filtered first. Okay, so it improves quite a bit. Here I show the kind of geometric flexibility that we have here. Okay, I must say that each of those fragments, okay, was used separately. Okay, we don't have here some group algorithms for detecting groups of root fragments together in this work once again. Okay, so it shows that it can be quite flexible. Okay, and also it shows here that the appearances and the appearances of the whole objects can be quite varying. And here I show the ROCs of the object recognition using, first of all, one root fragment. Okay? And here I use the set of fragments that are semantically equivalent to this one. Okay? And the same is here for a group of 7 root fragments. Okay? Eye, mouth, ear, nose, so on and so forth. Okay? Those that you saw in the images. And here I show the ROC of the group of if we had 7 root fragments, that it will be 7 groups of semantic representatives of the respective root fragments. And the blue or the green one here and here is also interesting, because we asked ourselves once again, what if we use a simpler algorithm, the algorithm of just detecting visually similar fragments? Because our visual similarity measure is tolerant enough, maybe. Okay, it detects some variations in the appearance. So maybe if we use the representatives chosen from this set, maybe the recognition performance does improve enough, and the semantic fragments do not bring any additional improvement. Okay, and the answer is no. You can see the green ones here do improve the recognition performance, but not as the blue ones do. Okay, so the conclusion so far are: first, semantic fragments can be identified by described algorithms for a variety of object classes. Okay, there are some cases, I will talk about them in a minute, where you cannot apply this very algorithm. Okay, you can apply something else that we devised. Okay, and the second conclusion is the representative sets of semantic fragments are more informative than representative sets of visually similar fragments. So now I have the fusion of these two ideas. Why not represent objects by hierarchy? But every node of hierarchy can be represented not as just simple, fragment, but as a set of semantically equivalent fragments. Okay? This, yeah?
So your fragments at each level do not overlap, or they can overlap?
Fragments at each level do not overlap. What do you mean? Fragments here?
Yes.
They can overlap. Yeah, they can overlap. Okay. The max-min feature selection algorithm will not let them overlap too much, because then the amount of increase in the mutual information will be low. Okay, but some increase can happen. Yeah, and it's a good thing too, because some redundancy is good for recognition sometimes. Yes, so this is the representation that we are striving to achieve, and there is some work to be done here. Okay, we are not there yet, but I've shown two ideas that kind of bring us closer to this kind of representation. And just a few minutes, okay?
You're fine. I mean, we have an hour and a half reserved, so just take your time.
Yeah. Okay. So anyway, it's very small.
Okay.
Okay. So let's suppose that we want to recognize images from two classes that are very visually similar. In general, fragment-based approaches published so far are not very good at this task. But one way to do it is the following. Let's suppose that Tweedledee here has a little scar under his eye, which Tweedledum does not have. For spoiling his new rattle. So we could use this little scar as our discriminative feature. The problem with this is if we use this scar, okay, and try to, in a novel image, which we do not know, is it an image of Tweedledee or Tweedledum, we just try to match the fragment containing this scar somewhere in the image. If our search window, our ROI, is a little too big, we can easily falsely match this scar with some feature here, for example, this wrinkle. This shows us that in order for such type of features, which are very, very simple features, like edges or small blobs or something like this. To be discriminative, we must pinpoint the exact location of this feature before we start searching for it. Okay? And the search window should be very, very small. How can we do it? The way that we propose, okay, and this is the teaser for our next paper for CVPR 2006, and we propose to do it by first locating some features that can be reliably detected in all the visually similar classes, for example, eyes or something like this, and then to kind of fix the position of the scar or whatever discriminative feature we have, small discriminative feature, okay, with respect to the position of the detected reliable features here. And why did I bring this topic here? Because it shows another type of relation. Okay? Previously, I showed you the relation of fragment and subfragment, okay? Where subfragments were good for detecting the fragments. Now, this is another kind of relation that also can be incorporated in the hierarchical scheme between, we call this one anchor and this one satellite. Because satellite is not helpful for detecting anchors. It's another kind of side relation. Okay? So it boils down to one line. There is more to hierarchies than I showed you today, and we'll try to find out even more. Thank you.